Okay, in this video I'm going to do this problem which has 8 parts, and in this problem we're considering the sets of even integers and odd integers. Even integers are any integers that can be written in the form 2 times some other integer. So we could say that the set of evens is the set of all x's that are integers such that there exists some other integer a such that x is twice a. Okay, so in order to prove something is even, an integer is even, all we have to do is write that, prove or show that it can be written as twice some other integer. Okay. Similarly, for the odds, all we have to do to show that an integer is odd is to show that it is of the form twice another integer plus 1. Okay, and I've gone ahead and written all of these answers out here. I've tried to make this video 3 or 4 times in a row without making a misstatement, and it doesn't seem to work, so I've just left them all written out here. The first one says that for all even integers, x plus 3 is even. And I'm thinking that if I take an even integer and add 3 to it, I'm going to get an odd integer. And I can, so I say this is false, and I'm going to consider x equals 2 as a counterexample. In order to prove a universally quantified statement false, all you need is one counterexample. So x equals 2 is our counterexample. It is even, however 2 plus 3 is 5, which is not even. Okay, so that's a good counterexample. For part B, it says there is some even integer x such that x plus 5 is 12. Well, I know the only integer that satisfies x plus 5 is 12 is 7, and 7 is not even. Okay, and so you might be tempted to write 7 is not even as your proof, but I want to see more than that in a proof like this, and we're going to prove this false by contradiction. We're going to assume it's true and show that we can come up with a contradiction. And so we're going to assume it's true, and then x is even. If this statement is true, then there is some x which is even, and x plus 5 is 12. So we're going to say, okay, let's suppose that x is even and that x plus 5 is 12. But then we know that x has to be 7, because that's the only integer that satisfies this equation. So now we have that x is not even. So now we have both that x is even, which, as I say, it's almost impossible to do this without making a mistake at some point. The x is even and the x is not even. And that's our contradiction. And so we conclude that the statement is false. Okay, so that's a more detailed proof that is a lot better and a lot more explanatory than just saying 7 is not even. So 7 is not even, just writing that down is not a proof here. Okay. If I move on to part C, it says it's not the case that there exists an even integer such that 2x is less than 5. Well, I can think of an even integer where 2x is less than 5. I mean an odd integer where 2x is less than 5. I'm going to choose 1. And in fact, what I'm going to do is I'm going to prove this statement false by proving its negation. The negation is that there does exist some odd number such that 2x is less than 5. And to prove an existential statement true, all you need is one example. So I'm going to choose x equals 1 as an example. Then x is odd, and 2x is 2, which is less than 5. Okay? Again, you can't just write 2 times 1 is less than 5 as your proof. You have to provide some written explanation as to what you're doing and to try to phrase it in terms of these valid proof examples that we've discussed. For part D, it says that for all evens, 2x is even. And in fact, we can make an even stronger statement that for any, so it's true, for any integer, For all x and z, 2x is even, and this follows directly from the definition of even integers. We don't have to do anything because it is of the form twice an integer. Okay. For part E, it's very similar. Part E says that for all odds, 2x is even, and that's true also because it's of the form twice an integer. Okay, so for part E, it's the same thing. It's true, in fact, again, for all integers, 2x is even, not just for all odds, but for all integers. And if I show that it's true for all integers, the odds being a subset of the integers, it's also true for all the odds. And this follows directly from the definition of the set of evens, where a number is even when it's twice another, an integer is even when it's twice another integer. Okay, let's move on to part F. F says it's not the case that there's an even number such that x over 2 is also even. And I think that's false because I think I can think of a case of an even number where x over 2 is also even, and I'm thinking of the number 4. 4 over 2 is 2, which is also even. And so what I'm going to do for part F is say that it's false, and I'm going to prove the negation. And the negation is the existential statement. And to prove an existential statement true, all you need is one example. So I'm going to prove the negation true by an example, and my example is x equals 4. Then x is even, and x over 2, which is 4 over 2 is 2, is also even. So I've shown by example that the negation is true, and therefore the original statement is false. And again, you could just say 4 over 2 is even and call that your proof, but that's not, although it gets to the crux of the matter, that's not a proof. You have to be able to explain your logic here. For part F, or for part G, it says that there is an even number such that x over 2 is odd. And I think that's true. I'm going to prove it by example. I'm going to use x equals 10. 10 halves is 5, which is odd, and 10 is even. So I'm going to go ahead and do that for part G. I say it's true by example, and I'm going to choose x equals 10 as my example. And then x is even, however, and also x over 2, which is 5, is odd. Okay? Finally, for part H, it says for all odd numbers, 2x minus 1 is also odd. And this is true, and this is another example where it's in fact true for the larger set of all integers. If it's true for all integers, it's true for all odd integers, because the odds are a subset of the integers. And so for all integers, 2x minus 1 is in fact odd. And we might have gone ahead and defined odds in terms of 2 times another integer minus 1, but we happen to define it as 2 times an integer plus 1. And so we need to put our odd number in the form of twice an integer plus 1 to prove that it's odd. And I can do that. I want to show that 2x minus 1 is of the form 2 times an integer plus 1. Well, I can rewrite 2x minus 1 as 2 times the quantity x minus 1 plus 1. And that is of the form 2 times an integer plus 1. 2 times an integer plus 1. And that works for all integers x in z, and therefore 2x minus 1 is odd, just the way 2x plus 1 is odd. Okay, so that, I hope, helps with this problem number 1 and gives you some good examples of proof techniques where the crux of the argument may be obvious, but it makes sense to write the proof down, fully explaining your logic and the technique of the proof that you're using. So I hope that helps.